It's good to be here, and we're almost at lunch. And just a little warning, just to prepare you. There's no monitoring in this talk, so hopefully you won't be too shocked. I first want to acknowledge the co-authors, and especially Lital Ozeri, who was really the ringleader in what I'm going to present. And so I collaborated with these folks. So I'm at Sac State. The rest of these folks are at the University of Haifa in Israel. And so the work I'm going to be talking is kind of one of the collaborations I had there while I was on sabbatical. And so I want to acknowledge the funding for this. I was in 2017 and 2018, I had a sabbatical and a Fulbright Scholars Program, supported my doing vernal pool research in Israel and in Morocco, and I did a little bit of teaching too. And so I want to definitely acknowledge Fulbright, also Leon Blaustein and the University of Haifa for being great hosts, and this is where the university is, looking over the Mediterranean. And then for definitely acknowledge Sac State for cutting me loose for a year. And so, of course, wildfire is a ubiquitous reality worldwide, and very common disturbance, as you can see from this map, in all ecosystems all over the world, and in particular in the Mediterranean region. So it's circled here, of course, California, Chile, South Africa, Southwest Australia, and then, of course, the Mediterranean region. And fire has, of course, diverse effects on ecosystems, and it's especially concerning in these Mediterranean regions because you have large populations living close to natural areas. In addition, of course, wildfire is iconic in the Mediterranean climates, especially because of the climates with the cool, wet winters, long, hot, dry summers and falls. And consequently, fire management and policy tend to be focused on protecting human property and life in these different locations. Of course, we've got outages that, hopefully this will work. So this is video that a colleague of mine, Dr. Jimmy Pitzer, took. This is up by Wheatland, over by Beale Air Force Base. So we know, we've been hearing about, on your way in this morning, about the outages that may happen, but we also use these, oops. Let's see if I can get out of that cycle. Okay. But chemical fire retardants really play an important role in protecting human safety and natural resources from very destructive fires. Their use has increased steadily since their introduction in the 1930s to aerially fight wildfires. And they're typically made up of fertilizing salts. This is the product used in Israel. Very common, very similar ingredients found in other products as well, where you have a lot of phosphates and iron and heavy metals in the product. And when these fire retardants come into contact with water, the retardant chemicals can be, of course, toxic to the aquatic wildlife and also alter water quality. And this even has resulted in the Forest Service having this policy of avoiding aerial application within 90 meters of water bodies. However, fire retardants do make their way into aquatic habitats, either through direct deposits, either accidental or intentional, or just through mobilization following after rainfall. And they can make their way into ponds and streams and other water bodies. And over the decades of the use of fire retardants, there's been a number of studies looking at how it affects aquatic organisms. And by and large, we see consensus on that they have negative effects on fish. They have variable effects on invertebrates. They tend to cause eutrophication in aquatic habitat. And there's some really interesting work by David Angler when he was based in Spain looking at kind of interactions between fire retardants and drought. And so they can interact with other environmental conditions in affecting aquatic habitat. But there's definitely many holes in our understanding of the effects of fire retardants. And there's been very few studies looking at the full food web in an aquatic habitat. There's been very few studies looking at the effects on amphibians. And finally, very few, surprisingly, studies looking at how seasonal wetlands and temporary ponds are affected by fire retardants. So the kinds of systems I work in are seasonal wetlands or temporary ponds. They're all characterized by these consistent dry phases. Of course, with our vernal pools here in California, fill up in winter and dry out by late spring. And worldwide, they're characterized, including here in California, by high levels of biodiversity and endemism, also high productivity and carbon sequestration, as well as being just more common in the landscape compared to permanent water bodies and less studied. Some people categorize the temporary ponds found in Mediterranean climates as being Mediterranean temporary ponds. And I just had to present this just to show you, give you an idea of how these systems look in these other Mediterranean regions. We have California here, the vernal pool, and then here is the vernal pool in Morocco. Here's one in Israel. They have very similar, it was just striking, just swinging a net through these ponds and finding, very similar species composition, and including, of course, you have fairy shrimp, but also tadpole shrimp in each of these regions, and as well as, of course, the salamanders. And so in Israel, it's the, which I'll be talking about today, the Near Eastern salamander, Salamandra inframaculata. In Morocco, it's the African fire salamander. Of course, we have the California tiger salamander here. So very similar communities, and so, and why I point out this, even though this work was done elsewhere, I had never really done work with the effects of fire retardants. I'm hoping that the work we did here will shed some light on the systems here in California, and I hope to extend a lot of this research here in California. So in these temporary ponds, they tend to have very simplified aquatic food webs, and this cartoon is even an oversimplification of a simplified food web found in these temporary ponds, but of course, we have the basal trophic level with algae and bacteria and so forth, protistans. Kind of the middle trophic level is made up of your insects and crustaceans, and then the top trophic level, and the one in the temporary ponds that we were working in was the larvae of that Near Eastern fire salamander. Of course, it gets more complex. You can have insect predators and so on, but we're not going to go into that territory during this talk. So when we approach aquatic food webs, ecologists tend to be interested in looking at what are the regulating factors affecting abundances in food webs. And two of the most common factors affecting these sorts of food webs are bottom-up and top-down forces. Bottom-up being and the effects of nutrients or resources. This could play into the effects of fire retardants, since there are quite a bit of phosphates in it. And so you can have an increase in phosphates, you would increase this basal trophic level, which may cascade to being translated to the upper trophic levels in increasing abundances. The top-down effects are really the effects of predators on the rest of the food web. And so you have these predator-prey interactions, and in some cases you could have trophic cascades where you have this negative predator-prey relationship here between the top predator and those middle consumers, but you also have this predator-prey relationship between those middle consumers and the basal trophic level, also a negative relationship. And sometimes in food webs you can have kind of the net effect is a positive effect on that basal trophic level driven by that top predator. And you probably know this as the trophic cascade. So basically the enemy of my enemy is my friend. Okay, but what we're interested in is kind of how do fire retardants play into all this? How do they interact with these food web interactions happening in these temporary ponds? And you can have these direct effects of fire retardants, but you can also have these indirect effects, right? It can influence kind of how predators affect the rest of the trophic levels, and even if it's affecting the basal trophic level, it can affect the other trophic levels as well. So we're kind of interested in these kinds of questions. So this study was a mesocosm project done at High Bar Nature Preserve right off the campus in Mount Carmel, Israel. These are 40-liter mesocosms, and Lital had 4 levels of fire retardant addition, and the fire retardants were diluted to 20% levels, and then based on LC50 levels, effects on the salamander, she manipulated these 4 treatment levels. And she sampled every 3 weeks. Okay, so let's look at some of the results. So when we look at the survival of the Near Eastern fire salamander, and I should point out that it's an endangered species there. This is the southernmost part of its range. And so it's of great concern for managers there. And what we see is that as you increase the level of fire retardants, survival decreases. And as it turns out, and I'm not talking about this today, but we did some laboratory studies and found that when you add more fire retardants, they stop feeding the salamanders. And so that was likely driving this pattern. And we also saw it with the time to metamorphosis, that as you increase fire retardant addition, it takes longer and longer for them to reach that metamorphosis. You can see them as little cutie pies right there. Okay, so let's go down to the next trophic level. So it's clearly negatively affecting that top predator in the system. Let's go to the next level of those middle consumers with the invertebrates. And what we find is kind of consistent with what's been found in other systems, that the responses are all over the place. I'm not going to dive into all the details, but there's, like for some cladocerans, they do best at those middle fire retardant levels. There's some that do best at the highest fire retardant addition levels. That brick red is the highest fire retardant addition level. And then you have things like the species of copepod, which does best in the control treatments, and they just get hammered by the fire retardants. And then the mosquitoes, they go gangbusters when you add fire retardants. They were just, and in fact, so this graph, it looks a little bit different, and is part of a different study. And actually, we just found out last week that it was accepted at ecological entomology. So we had this whole paper focused on mosquito effects. But here, they just do great at the highest levels of fire retardant addition. So we see all this variation in the responses of these species in the middle trophic level, and that translates into shifts in the community composition. And so these are a series of non-metric, multidimensional scaling plots. And so this top graph here is before we added the fire retardant treatments. And each of those polygons represents a different treatment. So here, even before we added the treatments, they're all overlapping right there. And over time, and following the addition of those treatments, we see this shifting in the community composition of that middle trophic level of crustaceans and insects. And it continues on. And I already pointed out this, mosquitoes tend to oviposit in those highest fire retardant treatments. Okay, and then at the basal trophic level, the bottom trophic level, where we measured everything from bacteria to cyanobacteria to algae and eukaryotes, other eukaryotes, we found consistent increases in the abundance of those organisms. And so I'm not going to go into all the details, but you can see on the x-axis is all fire retardant concentration, and they all tend to increase. The one rebel was bacteria free-floating in the water, did not respond, but everything else did. Okay, so to summarize, the responses of this community to fire retardants, we found this positive effect, this kind of bottom-up control of the basal trophic level, so positive effects on the bottom trophic level, variable effects in that middle trophic level, and a negative effect on the salamanders in that top trophic level. And laboratory work showed that they kind of stop feeding once you add fire retardants. And so you end up having this indirect effect on those invertebrates where what was once a negative effect is now positive. And there was no evidence from our work that there was a trophic cascade going on. So in conclusion, so this is one of the first studies looking at the whole community response to fire retardants. And we found that there were both direct and indirect effects of those fire retardants on this aquatic community. And certainly there's evidence from the study that showed that there's increased potential for eutrophication, especially when you're thinking about that pulse of phosphates coming in. And certainly we had evidence of that. But also increases in mosquito vectors. So those are some kind of negative, potential negative effects of fire retardants in this aquatic ecosystem. And for the most part, the work was consistent with previous studies, but certainly there needs to be further studies looking at the mechanisms, how is it affecting the physiology of these organisms, what's really at the heart of driving these direct and indirect effects in the system. And again, as I pointed out in the beginning, I'm hoping to kind of continue this work here in California on our seasonal wetland systems, and in order to ultimately better understand the environmental risk of applying these firefighting management tools. And conclude with a sunset from the Middle Atlas at a temporary pond. And thanks for listening.
Thank you. That was a great talk. I have a couple of quick questions.
Okay.
One is, how did the concentrations you used in experimental work compare with the concentrations you actually found, in some of these wetlands?
well, as Angela alluded to, it's kind of hard to get a take on that. Really understanding kind of that level, but we initially use a 20% dilution of the product, and then from there kind of use this use that LC50 level as kind of as a point of reference to determine the other ones. And so that's a great point, and we don't really know, and certainly to be able to get at that question and will help us calibrate, like, well, what are really the effects going on in these aquatic ecosystems?
Yeah, and the other question I had is, do you know chemically what might be causing toxicity, say, to the salamander?
Yeah, that's a great question, and none of us were physiologists, and so it's hard to tell. We trying to look into it and really didn't find anything. It's hard to tell whether it was something about the turbidity, because that's changing too, but it's odd because when you in these treatments, they stop feeding when you add fire retardants. If you were to pick them up and put them in fresh water, they're back to eating. And so we're not sure if it's a physiological response or behavioral, and so that would be a really interesting question to pursue.
I'm sorry if you answered this and I missed the comment, but you mentioned earlier that fire retardants are avoided to be applied within a 20-foot barrier of water bodies.
90 meters. So the Forest Service regulation is 90 meters from water bodies.
Okay, so my question is, if vernal pools are seasonal, wildfire season, I believe, is when they're dried out. So are they recognized as water bodies during that time?
That's great. Oh, that's an excellent question. I have no idea. But, probably not. I'll bet you most likely not. That video I showed, that's vernal pool territory in that area, and that was, I think, in August, and so that area was going to be completely dry, and even if there is water, you got to put out the fire, and so it happens. That's a great question.
I wanted to answer that question. The Forest Service maintains an interagency authority that maps where you're allowed to spray and not spray. And pilots have to observe those maps. So any pool that's at risk is on that map. And that doesn't mean that's the norm, that's the ideal. And so many of these areas that are off limits to be sprayed during the fire. And I also mentioned that the compound that was the coloring agent in Phosgene when it was owned by the Israeli company. It was iron oxide, that's rust. But many other companies and some of the phosgene that was used overseas had a different diet. For instance, there was an Arizona company that the Forest Service used that had iron cyanide, ferric cyanide that they used, and that could have toxic potential for the aquatic life.
Thank you for listening.